310.15b2 necessitates counting neutral conductors as current-carrying conductors if they handle more than half the unbalanced load current from any single phase. An exception exists for three-phase, four-wire, Y systems where nonlinear loads dominate. Nonlinear loads, like electronic devices incorporating rectifiers such as LCD screens and LED lighting, draw current in non-sinusoidal patterns. This introduces harmonics into the electrical system. Harmonics can amplify neutral current, potentially overloading neutral conductors. Given that LCD screens and LED lighting constitute the majority of the load, it is important to consider harmonic currents and the possibility of neutral conductor overload. The recommendation is to count the neutral conductor as a current-carrying conductor to establish a safety margin and avert potential neutral conductor overload. Furthermore, derate the neutral conductor as per the table in NEC 310.15b2 to diminish the risk of overload and ensure adequate sizing of the neutral conductor. Although the NEC exception might technically apply, it is judicious to exercise caution and treat the neutral conductor as current-carrying due to the substantial proportion of nonlinear loads in the system. This approach will bolster the safety and reliability of the electrical installation. To elaborate further on the implications of nonlinear loads and harmonics, it's important to delve into the specifics of how these loads generate harmonic currents. Traditional linear loads, such as incandescent light bulbs or resistive heaters, draw current that is directly proportional to the applied voltage. This results in a sinusoidal current waveform that is in phase with the voltage waveform. However, nonlinear loads behave differently. They draw current in short pulses or distorted waveforms, which contain harmonic components. These harmonics are multiples of the fundamental frequency, which is typically 60 Hz in the United States. For example, the third harmonic is 180 Hz, the fifth harmonic is 300 Hz, and so on. These harmonic currents can cause a variety of problems in electrical systems. Firstly, they can increase the overall current flowing in the neutral conductor. In a balanced three-phase system with linear loads, the neutral current is ideally zero. However, when harmonic currents are present, they can add up in the neutral conductor, leading to a significant increase in current. This increased neutral current can overload the neutral conductor, causing it to overheat and potentially fail. Secondly, harmonic currents can cause voltage distortion. The harmonic currents flowing through the impedance of the electrical system can create voltage drops at harmonic frequencies. These voltage drops can distort the sinusoidal voltage waveform, leading to problems with sensitive electronic equipment. Thirdly, harmonic currents can cause increased losses in transformers and other electrical equipment. The harmonic currents can cause increased heating in the windings of transformers, leading to reduced efficiency and a shorter lifespan. They can also cause increased losses in motors and other electrical equipment. To mitigate the effects of harmonic currents, several strategies can be employed. Firstly, harmonic filters can be installed to reduce the amount of harmonic current flowing in the system. Harmonic filters are typically composed of capacitors and inductors that are tuned to specific harmonic frequencies. These filters provide a low impedance path for the harmonic currents, diverting them away from the rest of the electrical system. Secondly, K-rated transformers can be used. K-rated transformers are designed to withstand the heating effects of harmonic currents. They have a higher insulation temperature rating and are larger core than standard transformers. Thirdly, oversizing the neutral conductor can help to prevent overloading. By increasing the size of the neutral conductor, it can handle a larger amount of harmonic current without overheating. Fourthly, using phase cancellation techniques can help to reduce the amount of harmonic current flowing in the neutral conductor. Phase cancellation involves connecting nonlinear loads in a way that cancels out some of the harmonic currents. For example, connecting single-phase nonlinear loads equally across all three phases can help to reduce the amount of third harmonic current flowing in the neutral conductor. Regarding the specific case of LCD screens and LED lighting, it is important to note that these devices typically have a relatively high harmonic content. This is due to the electronic power supplies that they use to convert the incoming alternating current voltage to the direct current voltage required by the screen or light emitting diode. These power supplies typically use rectifiers to convert the alternating current to direct current, which introduces harmonic currents into the electrical system. The level of harmonic distortion produced by these devices can vary depending on the design and quality of the power supply. However, it is generally safe to assume that they will produce a significant amount of harmonic current. Therefore, it is important to take the appropriate precautions when installing these devices, such as counting the neutral conductor as a current-carrying conductor and derating it accordingly. In addition to counting the neutral conductor and derating it, it is also important to consider the overall harmonic content of the electrical system. If the total harmonic distortion is high, it may be necessary to install harmonic filters to reduce the amount of harmonic current flowing in the system. The level of harmonic distortion can be measured using a harmonic analyzer. A harmonic analyzer is an electronic instrument that measures the amplitude and frequency of the harmonic currents and voltages in an electrical system. The total harmonic distortion is typically expressed as a percentage of the fundamental frequency. A high total harmonic distortion can indicate that the electrical system is susceptible to problems caused by harmonic currents. In conclusion, when dealing with nonlinear loads such as LCD screens and LED lighting, it is important to understand the potential for harmonic currents and to take appropriate precautions. This includes counting the neutral conductor as a current-carrying conductor, derating it accordingly, and considering the overall harmonic content of the electrical system. By taking these precautions, it is possible to ensure the safety and reliability of the electrical installation. Now let's delve a little deeper into the derating aspect mentioned in NEC 310.15b2. Derating, in electrical terms, refers to reducing the allowable ampacity of a conductor to account for factors that can increase its operating temperature. This is crucial because excessive heat can damage the conductor's insulation, leading to premature failure or even fire hazards. Several factors can necessitate derating. Firstly, high ambient temperatures can reduce the conductor's ability to dissipate heat, increasing its operating temperature. The NEC provides tables that specify derating factors for various ambient temperatures. Secondly, the number of current-carrying conductors in a raceway or cable can also affect the conductor's operating temperature. When multiple conductors are bundled together, they impede each other's ability to dissipate heat. The NEC provides tables that specify derating factors for different numbers of current-carrying conductors. Thirdly, the presence of harmonic currents can also increase the conductor's operating temperature. Harmonic currents can cause increased heating in the conductor due to skin effect and proximity effect. Skin effect is the tendency of alternating current to flow primarily on the surface of a conductor, which reduces the effective cross-sectional area and increases the resistance. Proximity effect is the tendency of alternating current to concentrate in certain areas of a conductor due to the magnetic fields produced by nearby conductors. Both skin effect and proximity effect can increase the conductor's resistance and therefore its operating temperature. To properly derate a conductor, it is important to consider all of the applicable derating factors. The derating factors are typically expressed as percentages. To determine the allowable ampacity of the conductor after derating, multiply the conductor's original ampacity by all of the applicable derating factors. For example, if a conductor has an original ampacity of 100 amps and is subject to a derating factor of 80% due to ambient temperature and a derating factor of 70% due to the number of current-carrying conductors, then the allowable ampacity after derating would be 100 amps times 0.80 times 0.70, which equals 56 amps. It is important to note that the NEC specifies the maximum allowable ampacity of a conductor. It is always permissible to use a conductor with a higher ampacity than required, but it is never permissible to use a conductor with a lower ampacity than required. Therefore, when derating a conductor, it is important to ensure that the allowable ampacity after derating is still sufficient to carry the load current. Furthermore, the type of insulation on the conductor also plays a significant role in its ampacity and derating requirements. Different insulation types have different temperature ratings, which affect their ability to withstand heat. Common insulation types include THHN, THWN, and XHHW. THHN insulation has a temperature rating of 90 degrees Celsius in dry locations. THWN insulation has a temperature rating of 75 degrees Celsius in wet locations, and XHHW insulation has a temperature rating of 90 degrees Celsius in both wet and dry locations. The NEC specifies the allowable opacities for different conductor sizes and insulation types. It is important to select the appropriate conductor size and insulation type for the application to ensure that the conductor can safely carry the load current and withstand the operating temperature. In addition to the NEC requirements, it is also important to follow any applicable local codes and regulations. Local codes may have additional requirements or restrictions that must be followed. It is always best to consult with a qualified electrician or electrical engineer to ensure that the electrical installation is safe and compliant with all applicable codes and regulations. Regarding the specific question of whether to count the neutral conductor as a current-carrying conductor in a three-phase, four-wire system with nonlinear loads, the answer is generally yes. Even if the majority of the load consists of nonlinear loads, it is still prudent to count the neutral conductor as a current-carrying conductor to provide an additional margin of safety. This is because harmonic currents can be unpredictable and can vary depending on the specific loads that are connected to the system. By counting the neutral conductor as a current-carrying conductor, you can ensure that it is adequately sized to handle any potential harmonic currents. In addition to counting the neutral conductor as a current-carrying conductor, it is also important to consider the size of the neutral conductor relative to the phase conductors. In some cases, it may be necessary to increase the size of the neutral conductor to accommodate harmonic currents. The NEC provides guidelines for sizing the neutral conductor in systems with nonlinear loads. It is important to consult these guidelines to ensure that the neutral conductor is adequately sized. Finally, it is important to remember that electrical safety is paramount. When working with electrical systems, it is important to follow all safety precautions and to use appropriate personal protective equipment. If you are not qualified to work on electrical systems, it is best to hire a qualified electrician to do the work for you. Neglecting to properly account for harmonic currents in electrical systems can lead to serious consequences, including equipment failure, fire hazards, and even electric shock. Therefore, it is essential to take the necessary precautions to mitigate the effects of harmonic currents and to ensure the safety and reliability of the electrical installation. Let's consider a practical example to illustrate the importance of counting the neutral conductor as a current-carrying conductor in a system with nonlinear loads. Suppose there is a small office building powered by a three-phase, four-wire, 208-volt Y system. The building primarily houses computer workstations with LCD monitors and LED lighting. The total load on each phase is approximately 100 amps. If we were to assume that the neutral current is negligible due to balanced loading, we might initially size the neutral conductor to be smaller than the phase conductors. However, given the prevalence of nonlinear loads in the form of computer power supplies and LED drivers, a significant amount of third harmonic current is likely to be present. This third harmonic current will add arithmetically in the neutral conductor, potentially exceeding the ampacity of a smaller, undersized neutral. If the neutral conductor is undersized and overloaded, it can overheat, leading to insulation damage and potentially a fire. Moreover, an overheated neutral conductor can increase the voltage drop on the neutral, which can cause malfunctions in sensitive electronic equipment. By counting the neutral conductor as a current-carrying conductor and applying appropriate derating factors based on the number of current-carrying conductors in the raceway, we would likely select a larger neutral conductor that is capable of safely handling the expected harmonic currents. This would significantly reduce the risk of overheating and voltage drop, ensuring the reliable operation of the office equipment and enhancing the overall safety of the electrical system. Furthermore, the use of harmonic filters could be considered to further mitigate the effects of harmonic currents. Harmonic filters are designed to reduce the amplitude of specific harmonic frequencies, thereby reducing the overall harmonic distortion in the system. This can further reduce the stress on the neutral conductor and improve the efficiency of the electrical system. In addition to harmonic filters, other mitigation techniques can be employed, such as using power factor correction capacitors to improve the power factor of the system. Power factor correction capacitors can reduce the amount of reactive power flowing in the system, which can also help to reduce harmonic current. The selection of appropriate mitigation techniques will depend on the specific characteristics of the electrical system and the nature of the nonlinear loads. A thorough analysis of the system is essential to determine the most effective mitigation strategy. In any case, it is always prudent to err on the side of caution and to count the neutral conductor as a current-carrying conductor in systems with nonlinear loads. This simple step can significantly improve the safety and reliability of the electrical system and prevent potentially costly and dangerous problems.